I want to do an example utilizing torques and angular acceleration, adding to it forces and accelerations to see how they link together. To do it, I'm going to put together, let's say, a mildly unpleasant Atwood machine. So I have a system of pulleys that are fixed relative to each other. One has a radius of R1. The other one has a radius of R2. And so the R1 is, we'll say, is 1.2 meters, and R2 is 0.4 meters. Now, there are masses hanging off each of these pulleys. So there's a string wrapped around the inner pulley, and hanging off it is a mass we'll call M2. And there's another string wrapped around the larger pulley, and it's attached to a mass we'll call M1. And remember, these pulleys themselves are fixed relative to each other, so they rotate at the same rate. So, well, let's say M1 is equal to 24 kilograms. We're going to say M2 is equal to 36 kilograms, and luckily we just know the moment of inertia of the whole object is equal to 40 kilograms meters squared. We don't have to calculate that. We know that initially. So, what is the angular acceleration of this system, as well as the accelerations of the masses and the tensions in the string? So we'll call this a tension 2 and a tension 1. Okay, well, what sort of forces, what sort of physics could we apply to this problem? We have a pretty good picture and a setup now. It looks like I'm going to need to know the forces on the object, so I'm going to apply Newton's second law, as well as doing a torque analysis, torques and angular accelerations, say for the pulley about the center. So I'm going to just sort of apply all of this physics and sort of a brainstorming to see what sort of relationships I can come up with between the things that I know and the things that I don't know. All right, so I'm going to start with mass 1. And I'm going to look at all the forces on mass 1. So what are the forces on mass 1? There's force due to gravity. That's down, and there's the tension 1 in string 1, and that's up. All right, let's establish a coordinate system. Mass 1 is not as heavy as mass 2, but it's further out. I'm going to choose down. I'm going to guess, and if all my accelerations end up negative, then I can change it around. I'm going to guess that mass 1 is going to go down, and so I'm going to choose, just for my convenience, the positive to be down in this case. So that means that the magnitude of the gravitational force, the component of the gravitational force in this direction is the positive magnitude of the force, minus then the magnitude of tension 1, because it's going to be in the opposite. This is my x here, the negative x direction, is equal to the mass of this one object, mass of 1, times the acceleration of this one object, acceleration 1. Okay, and then I know that this is the force of gravity on this object is m1g, so minus t1 is equal to the mass of 1 times the acceleration of 1. All right, fine. Let's go take a look at mass 2 now. Mass 2. And so what are the forces on mass 2? Well, okay, same thing. The force due to gravity as acting on mass 2, as well as the tension in the string, which is up. I'm going to choose my positive axis up for this one, just because I think that it might go that way when released. I don't know that for sure, but I'm going to guess that. And so given this choice of coordinate system, then the magnitude of the tension force is positive has a positive, is the positive component in my positive x direction. And the magnitude of my gravitational force is pointing in the negative x direction, is equal to the mass of this one object, m2, times the acceleration of this one object, a2. Okay. And so, so here, now I have relationships between these objects. What's the relationship between a2 and a1? Well, they're not necessarily the same because they're not connected by a single string. So I don't have anything to say about that just yet. Okay, so let's look at a torque analysis. Okay, so what are the... I'm going to do a torque analysis now, and we're going to look for torques on the pulley. So we're going to do about the center of the pulley. So we're going to say right here in the center, and we're going to look at doing the torques. Okay, so what are the forces now on the pulley? So if I draw sort of a box around my pulley, the forces are T1 and T2 forces, and also then there's the contact force, which I'll call, then just call that F, the contact force of the axle. Right? So there's some axle that around which this thing is rotating that the pulley is resting on, and that's attached to the wall, say, or something. And so there's some force of the axle here on the pulley. All right. So now let's look at the torques for each the torques for each force. Okay, I need more space here. So the torque for the axle is equal to R cross F, where R is the vector from the axis of rotation to where the force acts, which thankfully, I forgot there's also the force due to gravity on the pulley, of course. But back to the torque due to the axle, the force due to the axle is acting at the point where we're evaluating our torques, right? We're evaluating our torques about the center. That's where the axle is. So that's the point where the axle force acts. So the torque due to the axle is 0. By the same token, the torque due to gravity, which is R cross F, so the gravity acts, well, F sub g, of course, the gravitational force. Well, this is the gravitational force on the pulley. The gravitational force on the pulley acts at the center of the pulley, which is where we're evaluating our torques. So the torque due to the gravitational force is also 0. So that's just the only torques that lead to an angular acceleration for my pulley about the center of mass of my pulley. That's where the axle is the torques due to the tension. Okay, so the torque due to tension 1 is going to be, we'll call R1 cross tension 1. Okay, so what does that equal to? So tension 1, which is here, to the point where it acts. So the tension 1 comes into, it makes contact with the pulley at essentially this horizontal line, because this is the point where it leaves. So this tension makes contact right at this point on the pulley. And so the magnitude of this is R1 vector. The magnitude of this R1 vector is just the radius, the outer radius of the pulley, that's R1. And it makes a 90-degree angle with the tension force. Right? If I were to do a free body diagram of the pulley, I would have, well, there's a contact force, obviously, that's this force due to the axle is up. There's a gravitational force that's down, and tension 1 down, tension 2 down, right? All force of gravity plus all the tensions, they all exert a force that's down on the pulley, right? Okay, so the radius of this R1 makes a 90-degree angle with the tension force from 1. So this is equal to the radius of 1 times the tension of 1. And now we need a direction. So we need a coordinate system for this. So if I set up a coordinate system, say, where here's plus x and here's plus y, I do a right-hand rule where my index finger goes along R1, my middle finger then goes along tension 1, which is down, my thumb is pointing out of the screen, out of whatever you want. Well, given a right-handed coordinate system, my positive z-axis must also be out of the screen. So the torque is out of the screen, so this induces a positive rotation for the torque. Okay. So now, if we do the same thing for the torque due to tension 2, that's equal to R2 cross tension 2, where R2 is now the vector that points from the axis of rotation to the point where tension 2 acts. Okay. Well, tension 2 acts at the point where the rope makes contact with the pulley, which is a distance R2 away, and it makes a right angle, 90-degree angle, with the tension force. Right? So the cross product then, since they're at right angles, just gives me the magnitude R2 times the magnitude tension 2, and the sine theta is 1. So now if I want to look at the orientation, then if I put my index finger along R2 and then my middle finger down, then my thumb is pointing into the screen, and that, given my right-handed coordinate system, gives me a negative rotation. The rotation gives me a vector along the negative k-axis. Okay, so now if I sum all my torques, okay, so that gives me a R1 T1 minus R2 T2 in along the k-hat to the z direction. Okay, and so the sum of the torques then gives me a moment of inertia times magnitude of my angular acceleration that will also be oriented such in the positive k direction. So now if I just turn that into my components, this component must be equal to this component. I get R1 T1 minus R2 T2 is equal to the moment of inertia times alpha. Okay, so I want to find alpha. I know I know my radii. I don't know T1 and T2, so I have 3 equations, but I have 3 equations and 5 unknowns. These equations, I have T1 and T2, which are also unknown, but I also have A1 and A2, and they are also unknown. All right, so we need to be able to link A1 and A2 to my angular acceleration. So how do I do that? Well, I go back and I use what I know about sort of rolling without slipping. So again, instead of, I don't have a cylinder rolling without slipping around the ground, but I have a rope which is the sort of my rotating cylinder is rolling without slipping, given that my rope is not slipping along the object. Okay, and so what that tells me, let's say go for my mass 1. If my mass 1 is decreasing with an acceleration a1, that acceleration is equal to the tangential acceleration of a point along the surface. And that's my rolling, essentially my rolling without slipping condition. Given that my rope is not slipping, the linear acceleration a1 of the rope, and thus the mass m1, is equal to the tangential acceleration of a point on the outer part of the cylinder. And then we know, given our vector description of rotational motion, that that tangential acceleration is equal to the angular acceleration alpha times r. So we'll bring this sort of down here. We know that the linear acceleration a1 is equal to the tangential acceleration at r1. This is the tangential acceleration at r1, the tangential acceleration of a point at r1, the outer point of the cylinder. Well, that just is equal to the angular acceleration times r1. Okay, so that gives me another relationship between my variables a1 and alpha, angular acceleration times the acceleration of mass 1. So now I can do the same thing on the other side. If mass 2 has an acceleration a2, okay, that is the same as the tangential acceleration at the outer point of the inner cylinder. Okay, and that outer point of the inner cylinder is just equal to the angular acceleration alpha times the inner radius, which is r2. So if I bring that down here, we have a2, then this is the acceleration of mass 2. That acceleration of mass 2, which is the same as the sort of acceleration of a point on this rope, that is equal to the acceleration of a point at the outer point of the cylinder at r2. That's my rolling without slipping condition, my no slip condition. And so that then is equal to the angular acceleration alpha times the radius at that point, which is r2. So this now gives me another relationship between the acceleration and my angular acceleration. So now I have 5 equations, 5 unknowns, and I can go ahead and solve. Okay, so if I start with my my forces, I'm going to take these and solve each one for my tension. So from the first one, I get T1 is equal to m1g minus m1 times the acceleration of 1. And T2 is equal to m2 times the acceleration of 2 plus m2 times the acceleration due to gravity. So now I can substitute both of these into this expression, and I get m1g minus m1a times r1 minus, then substitute in for T2, m2a2 plus, this is a1, m2a2 plus m2g times T2 is equal to I alpha. Okay, so now I can substitute in for A1 and A2. So that's going to then give me, and I'm going to multiply through. So my first term is M1 GR1, and that's minus then the second term, which is M1 R1 squared alpha, because I substituted in R1 alpha for A1. That's here, R1 alpha for A1 into here, so I get M1 R1 squared alpha. So this is minus, then, this term, oh, sorry, this is R2. This should be, let's fix that. Times R2, right? And so then the second term, this I'll substitute in alpha R2 for A2, alpha R2 for A2, and this becomes M2 R2 squared alpha then minus m2g r2 I alpha. Okay, so I want to solve for alpha, so I have to combine the terms. So I'm going to bring all the terms with alpha together on the right-hand side. And so then I have m1 gr1 minus m2 gr2 is equal to, and then everything on the other side I get I plus m1 r1 squared plus m2 r2 squared times alpha. Okay, so if I were to just solve for alpha over here, then I get m1 gr1 minus m2 gr2 divided by this whole thing, which is I plus m1 r1 squared plus m2 r2 squared. Now's a time to look at this. Does this make physical sense at all? What does this top really represent? m1g r1 times m2g r2. Well, m1g, that's the gravitational force of this. m1g r1. So that's sort of the torque that this mass is putting on the cylinder at this point, trying to rotate it counterclockwise. Okay. And so this minus m2g r2, so that's the torque due to mass 2, m2g, the force due to gravity on g. That's the force it's pulling with, and times r2, so it's the torque that m2 is applying to the cylinder, trying to rotate it the other way, trying to rotate it clockwise. And so that makes sense. So the difference between the torque that mass 1 is applying and the torque that mass 2 is applying is going to lead to the angular acceleration. And so this denominator then is essentially the resistance to that net torque. So this is the sort of the resulting net torque of the problem, the torque of mass 1 is trying minus the torque of mass 2. And then this is the total resistance to that net torque. And it represents the moment of inertia of the cylinder itself plus a term that looks like, m1r1 squared. So that's the sort of a moment of inertia associated with mass 1, and then there's another term, m2r2 squared, that looks like a moment of inertia of mass 2. So what that's telling you is there's a contribution to the resistance of the rotation associated with the mass, that if the larger that these masses are, the harder it is for any net torque to induce a rotation of the entire system. So this all makes makes physical sense, these terms and how they combine, which is why it's so important when you solve complicated problems like this. You don't plug in numbers. You always keep your terms till the end, so that when you get an expression like this, you can evaluate, you can look at the different terms in your expression and see, do they make physical sense? Are they contributing in the way that is logical given the context of the problem? Okay, so I think it is, so we can go ahead. These are now all known parameters, and we can plug in those values. I'm not going to go through the arithmetic, but when I get a result of 1.37 radians per second, when I plug in all those numbers, and you can check that. And once I have this, I can now solve for everything else. The acceleration of mass 1, which is alpha r1, I get to be 1.644 meters per second squared. Well, the first thing I should point out is I was right. This is a positive number, which means the entire system is rotating counterclockwise to induce a rotation in the positive k orientation. Okay, so my acceleration of mass 1 is 1.644 meters per second squared. My acceleration of mass 2, alpha r2, that gives me 0.548 meters per second squared. So again, these are both positive, given how I defined my coordinate system for each mass. Mass 1 is accelerating down, mass 2 is accelerating up, and mass 1 is accelerating much faster, has a larger acceleration than mass 2. The acceleration of mass 2 is much lower, so it accumulates a much lower velocity over time. And so that's the accelerations of the two mass. Then I can find the tensions in each one if I want, given these expressions here. And if I just plug in those numbers now, I get tension 1 of 294 newtons and tension 2 of 746 newtons. So tension in 2 in here is much larger than the tension in 1. But because it's acting on a much smaller radius, 1/3 the radius, it doesn't exert as much of a torque as tension 1 does, and so you still have a net rotation in the counterclockwise direction.